Okay, so it says ropes 3 meters and 5 meters in length are fastened to a holiday decoration that is suspended over a town square. The decoration has a mass of 5 kilograms. The ropes fastened at different angles make angles of 52 degrees and 40 degrees with the horizontal. Find the tension in each wire. So what are you finding? Find the tension in each wire and the magnitude of each tension. What does that mean? What are they asking for? The direction and magnitude. The direction and the magnitude. That is correct. They're asking for the direction and the magnitude. So is this star moving? Danny?
It's not hitting anymore.
Yeah, right. It doesn't say this thing is falling down. It'd be a pretty crappy hanging job, right? So that means that if it's not, is it moving side to side?
No.
It's moving up and down. So that means that it's in equilibrium, meaning the entire force going down is equal to the entire force pulling it up, and the same thing horizontally, right? Got it. Okay, so we have to write some equations to describe the forces that are acting upon this star.
Equals
So we have
line over 5.
cosine of what?
40.
Equals?
That line you just draw, we need to label it. Q.
SQ.
What? SQ over 5.
Sure. So then, therefore, what do you get from that? Where do you go from here?
5 cosine 40 equals SQ.
Yeah, so SQ is?
Wait, what do you have? 5 in there? 5 is length. It's not the force.
I know. I'm asking you here. I'm just following. I'm doing what he's telling me to do. Okay, so we have an issue here. What can we set up now? We know that t cosine 40 degrees is equal to, t cosine 40 degrees is equal to what?
Negative.
Nope.
H.
Oh yeah, sorry, excuse me. Plus, you're absolutely right, Josh. H cosine 52 degrees is equal to 0. Are we okay with that?
But those should be TX and HX.
TX, I'm sorry, TX, yes, TX and H. No, this is exactly what it's supposed to be, right?
Yeah.
We're adding TX and HX together, and TX and HX are those things on the left. That is correct. Now what's the second equation I can write? What's the second equation I can write? Jefferson.
You can set up the same thing, so you'll have h of y plus...
No, don't say H of Y. It's not H sub Y or HY.
Plus
Yep.
t sub y equals 0.
TY plus HY is equal to?
0.
Nope.
No? Oh.
50.
Oh, 50 newtons.
Right?
Excuse me. Yeah.
50. Close. So now we can write T sine 40 degrees plus H sine 52 degrees is equal to 50. So we have a system of equations. How many equations do we have? How many variables do we have? 2. Yes.
Question.
Shoot.
T and H have different directions, so...
T and H have different directions.
No, I mean, like, the component of TX, like, component of T and component of TX and TH...
Vectors, they're written in what kind of form are they written in right here? This is in
Component.
component form. The dot product is literally the sum of the product of the corresponding pieces of the component vectors. It always comes out to be, so if I gave you one vector and another vector and I said find the dot product is always going to be what type of number? It's always going to be a scalar. It's always going to be a scalar. Absolutely. It's always going to be a scalar. It's always going to be a scalar. Yes, Josh?
I was working with Mr. Vile's lesson. He mentioned the term linear, is linear independence the right term?
That is a term in math, yes.
Is that the same thing? Is that basically what we're doing
No.
with the dot product?
Please stay on topic. There's a million different ways we can get off topic here. It's like saying a wavelength and a color and then saying a number. Yes, those are all related entities, but let's stay on this. Okay, it's always a real number. It's always a scalar. Scalar product, sometimes called an inner product. Some basic rules about dot products. If you take the dot of a vector times itself, what do you end up with? What does this represent right here?
The magnitude squared.
The magnitude squared. That is correct. It's the magnitude squared. What does this tell us on number 2? What's this tell us on number? What does this tell us on number 2? Yeah.
It doesn't matter which order you multiply them in.
We're not multiplying.
Or adding their components multiplied together.
Yeah. Well, it doesn't matter what order you do the dot product in, is what you can say. That's totally fine, and that should make logical sense because if you break a dot product down, all it is summing real numbers and multiplying real numbers. We know that multiplication is commutative in real numbers, so you're all set. What does this essentially say right here? If you have the sum of two vectors, you can dot it. What can you do with the dot product? You can, what's the word I'm looking for?
Distribute
You
it.
can distribute it, absolutely. And the scalar does exactly the same thing. The scalar does, you can put the scalar anywhere you want as long as it's only being multiplied by once. And then if you hit anything with the zero vector, what happens?
Zero.
It's 0, absolutely. Okay. This is where it gets to be fun. Okay. Get to do some math here. Our first really useful, potentially new thing. Let's just, I could do a poll by hands here. How many people have seen this before right here? Dot product of two vectors is the magnitude of each times the cosine of theta, where theta is the angle between the vectors. You've seen that before? Yeah, it's something that is really, really, really useful. Let's see if we can figure out where that comes from. First of all, what does it mean by the angle between? If you have two vectors.
They have to be starting at the same point.
Ho, what's it mean? What's it mean, angle between? Yeah, if I have two vectors, 2 space and 3 space. Okay, so what can we do with this? Well, we can isolate cosine. What's cosine theta equal to? A cross A dot B over magnitude of A, magnitude of B. So let's take a look at what we can do with this. On this right here, what is theta equal? Cosine inverse of
That.
this. Exactly.
That.
So this is helpful. This allows us to find
Angles between.
the swept out angle. Absolutely. Great. Okay. Let's say I gave you, I don't know, A is equal to 1, 2, 3, and B is equal to 4, 5, 6. What's the angle going to be between them? It's going to be theta is equal to cosine inverse of what? 4 plus 10 plus 18, which is?
32.
Yep. Over, see how many of these numbers we can do in our head. We have to square, oh man, we have to do the magnitude of 1, 2, 3, so it's 1 squared plus 4 plus 9. So it's going to be 14. Square root of 14 times the square root of 36 plus 25 is, 36 and 25 is? 61. 61 plus 16 is? 77. This will be square root of?
77.
How did you get that?
How did I get that? Right there. So what is 32? 32 is the dot product of A and B.
4 plus
4 plus 10 plus 18. We're good with that? How did we get, what's root 14? The square root of 1 squared plus 2 squared plus 3 squared. And what's the square root of 77? That's the square root of 16 plus 25 plus 36. Do you do this by hand? No. This should be a automatic on you're typing by sight, you're all set. Okay. What happens though, this is the first big question, what happens if the angle between the vectors is pi over 2? What happens to the corollary if the angle between, when I say the corollary, I mean this right here. What's cosine of,
0.
yeah, that is a noun, that's correct. Cosine of pi over 2 is 0. So what happens to the corollary here? So, what?
Would it fail? Or
No, let's see what happens here. Cosine of pi over 2 is 0, right? So 0 is supposed to be A dot B over this right here. What's the only way for a fraction to be 0? The top, the numerator has to be 0, right? So we now have a nice statement. Two vectors are, what's the word I'm looking for here?
perpendicular?
We're going to use the big kid word for it. Begins with an O. How many people have seen that before? Orthogonal? Yay, you're learning something. All right. Yeah, SAT vocabulary. Two vectors are orthogonal if and only if their dot product is 0.
orthogonal is the same thing as perpendicular?
That is correct.
Different word.
It's English.
That's true.
We have a whole book called like a thesaurus that by definition gives you multiple words that mean the same thing. Okay, here we go. So, if and only if. Does anybody know what the symbol for that is? There's a simpler. I wish I knew how to do that. The one I'm thinking about is this. Arrows, but also this. There's that or this. use one of those. Mathematicians have certain words they use over and over and over again. Okay? Over and over again. Okay, so that's our first corollary. That's nice. So what does the angle between the two vectors have to be if A dot B is 0? The angle between them has to be
Pi over 2.
pi over 2. It has to be 90 degrees. Exactly. That's what we've proven, and this is what we just wrote here. Two vectors A and B are orthogonal if and only if their dot product is
0.
0. Excellent. Okay. So if I gave you this question right here, how do you prove quickly that these two vectors are orthogonal? You find their
Dot product.
yeah, and that literally is going to be 2 times 5 plus 2 times
-4.
plus -1 times 2. That's going to be 10 minus 8 minus 2, which is...
0.
So is it pretty easy to find out if they're perpendicular or not? Yeah, it's pretty easy to figure that out. That's nice. What happens if the two vectors point in the same direction? What happens if they're pointing in the same direction? What's the angle between them?
0.
0.
The angle between them is
0.
0. Yeah.
0 is 1.
What?
Cosine of 0 is 1.
Yeah, so just remember these things. If they're pointed in the same direction, or if they're perpendicular, the answer is going to be generally nicer. Yeah, a little bit. Okay. Big point of terminology here, the direction angles, and here's a picture that I cannot draw very well, so I clipped it in, okay? Here's the picture right here. Here are the direction angles. So there's a vector A right there. Do you see it floating in space?
Yep.
These angles, alpha, beta, and gamma. So alpha is the angle swept out from the x-axis to A, directly to A. Beta is the angle swept out from Y to A. And gamma is the angle swept out from the z-axis to A. We now have a formula that allows us to find the angle swept out between two vectors, right? We have a formula that allows us to do that. So, for example, if I had a vector like this and another vector, I'm going to pause this for 1 sec because I need to go off.
J.
You want to do J? Okay. So if we do J here, we know that cosine theta is going to be, and J is the y-axis, so it's actually going to be which angle in terms of this diagram?
Beta.
Beta, thank you. So cosine beta is going to be A dot I all over what? A. Oh, we wanted J. I'm sorry. Thank you very much. J over this, right? Correct?
Yeah.
What is the magnitude of J?
1.
So we have A dot J over A, right? The magnitude of A, if A, we're going to generalize A. If we that could be A, right? But if we wanted to generalize A, what would the values were? We'll call it A1, A2, and A3. If you multiply a vector A times the J vector, what are you just left with? A2 over the magnitude of A. The only lesson I want you to take from this is, in multivariable calculus land, things can blow up in your face, but they can also do what nicely? They can collapse really nicely. So in this case, we know that beta is equal to cosine inverse of what? A2 over alpha A. Are these directional angles going to be important in later questions? Yes, absolutely. These directional angles will be important. Now, does the work change at all if you go for K or for I?
No.
No. Instead of A2, what's it going to turn into?
A1.
A1 and A3. And the Greek letter will change at all. That's the only